The next trend we want to talk about is called ionization energy. Ionization energy is specifically referring to the amount of energy needed to remove an electron. So when we say ionization energy, we really mean cationization energy, because cations are the only ones that have electrons that get lost. So typically we're talking about metals and the metal ionization energy, but you can also discuss the ionization energy of nonmetals too. But we are looking at the removal of an electron. Now let's take a look at magnesium as an example. Magnesium's first ionization energy would be the amount of energy needed to remove the first electron from magnesium. And that number is usually represented in amount of kilojoules per mole. So 735. And this number is going up or going down. The higher it is, the more energy, and the lower it is, the less energy. Now the second ionization energy, as you'd expect, would result in more energy. Because remember, the removal of the first electron results in a smaller radius, because we have now 12 protons in magnesium's case pulling on 11 electrons. So when we're going to remove the second electron, we're going to try and add more energy to it, and it's going to need more energy to remove another electron, because we have 12 protons pulling on 11 electrons, so we need even more energy, because it's already smaller compared to its parent, and it's going to need even more energy to get it down to a +2 charge. And so ionization energy increases the more electrons you try and remove. But check out this jump. If you're going to go from a +2 magnesium to a +3 magnesium, look at how much more energy it takes. And what's happening here is, as you remove the first two, remember magnesium has 2 valence electrons. So the first one's kind of hard and the second one's even harder yet. But to remove the third electron, you are now going to need to remove from a core electron, no longer a valence, but you are now inside the valence electron shell, and you are now looking at the core. And the number jumps significantly when you try and remove a core electron. So in summary, it's fairly easy to remove valence electrons, but the energy jumps significantly when you start to talk about a core electron. Here's a really good picture that describes this. So you've got elements here down the left-hand side, and these are all elements of the second period of the periodic table. So sodium, followed by magnesium, aluminum, and so on. You're going from left to right. Now the first ionization energy of sodium is its valence electron, but then it jumps 10 times to remove its second, because the second ionization energy is 1 from the core. Now magnesium, as we just saw, it's fairly difficult to remove an electron, and it goes up to the second, but really high on the third, because you are now trying to remove a core electron. Aluminum's got 3 valence electrons. The first one's kind of difficult. The second one more difficult because it's getting smaller. The third one more difficult yet because it's getting smaller. And then it jumps to 11,000 kilojoules per mole. Again, because we're trying to remove a core electron. And as you can see, the stair step starts to emerge. That as you get to the last valence electron, it's pretty high, but then the next one after the last valence is the highest yet. And that pattern emerges all the way across the period in the periodic table. It says right here, note the largest jump in ionization energy is going from the removal of a valence electron to the removal of a core electron. So let's talk about the general trend of ionization energies on the periodic table. In general, as we go across from left to right, the first ionization energy increases. Now that's the amount of energy needed to remove just the first electron of an element. And it increases as you go to the right. Well, why? Well, one reason is because the elements are getting smaller, so it's harder to remove the electrons. But then you have to say, well, why are they getting smaller? Well, as you move from left to right, the elements are holding onto their electrons more tightly due to a stronger effective nuclear charge. And because of that, you find it more difficult or higher energy to remove the electrons from a smaller atom. It's hard to remove electrons from a smaller atom, and so you need more energy. It's kind of like a football player running down the field with the football hanging out in his arm or her arm. If she happens to be holding the football player far away from her body, the defender can come in and easily dislodge. The further away the electrons are, the easier they are to dislodge. It doesn't take a lot of energy. But the tighter you hold the football to your body, the more difficult it is to remove, and the harder the hit needs to be in order to dislodge that electron. That is similar to the way electrons are held tight to the nucleus, how a football is held tight to a running football player. But simply just saying a smaller atom is harder to dislodge the electron is not enough to get full credit on the AP test. You need to say, why is it smaller due to effective nuclear charge? What causes the small atom and the high ionization energy? That's what we're looking for in types of questions like that. Let's take a look at this picture because it's got 3 dimensions. It's got vertical, horizontal, and some depth component to it as well. It's kind of hard to make out because of the depth component, but I think it's still cool nonetheless. So you increase ionization energy going to the left across a row. Take, for example, the second period. Lithium 520, beryllium 899, and then it goes to 801, 1014, and so on and so forth. So the general trend, now there is some up and down movement to this, and we'll talk about that here in a little bit, but the general trend is it increases as you go to the right. You'll also find an increasing trend going up a column in the periodic table. Once again, your bigger elements are at the bottom, and those are easier to remove electrons from. And as you get going up a column, they are smaller and smaller and smaller, more difficult, more difficult, more difficult. Now, why are they getting smaller going up? Well, because you were removing energy levels that could contribute to electron shielding. Eventually, you get to the top where there's little to no electron shielding, resulting in very, very small elements at the top. The same is true with this column: bismuth, antimony, arsenic, phosphorus, and nitrogen. The trend is it gets more difficult to remove an electron going up because nitrogen's the smallest here because it experiences the least amount of electron shielding compared to phosphorus. Now, there are some anomalies to the ionization energy trends across the periodic table, and it's important to know these because these are possible questions on the AP test. Now, what are these anomalies that I'm speaking of? Well, I'll show you on the next slide. I'll bring that picture back. But a full orbital is favored to a partially full orbital, even though a partially filled energy level may have a smaller atomic radius. It has to do with stability. A full orbital is in fact more stable, and as a result, it is higher ionization energy than, say, a partially filled orbital in an element right next to it. The 3 examples that I'm going to highlight are beryllium compared to boron, magnesium compared to aluminum, and zinc compared to gallium. Let's first take a look at beryllium, which is 899 compared to boron. Beryllium is a full S2. It's full at 2s2. But boron has a 2p1. Now, as we talked about in the last slide, a full orbital is more stable than a partially filled orbital. It's more stable, so it needs more energy to dislodge. Another one you'll see is the 2 elements right below it, magnesium and aluminum. Magnesium 738, that's a full 3s2, but aluminum is a 3p1. This is less stable because aluminum has 1 electron in the p orbital and is easier to dislodge. Aluminum's got a smaller radius, and you'd think it'd be more difficult to dislodge that electron, but in fact, it's more difficult to dislodge magnesium. So far, we focused on the barrier between the s orbital and the p orbital. But let's take a look at the barrier between the d orbital and the p orbital because it shows up here in zinc and gallium. Zinc is a full 3d10. And then you move to the 4p1 and you'll see a significant drop, almost by half. Not quite by half, but a significant drop. Because zinc is a full orbital and gallium is a partially filled orbital, zinc is more stable than gallium and thus it has a higher ionization energy. In general, ionization energies decrease going down a group, and we already talked about this because they get bigger going down, and so bigger atoms have lower ionization energy. Bigger atoms exhibit more electron shielding. More electron shielding results in bigger atoms. Bigger atoms need less energy to remove the electrons. So let's take a look at 2 elements and ask ourselves which one would have a higher ionization energy. So find sodium, number 11 on the periodic table, and it is located on the far left-hand side. It's in the 3rd row, so it's over here. Chlorine is in the same row, but it's all the way on the other side. It's number 17. As we said, the trend says that ionization energy increases as you move to the right on the periodic table because you have a smaller element with stronger effective nuclear charge and higher ionization energy. So to answer this question, the correct answer is chlorine. Chlorine has more energy to remove an electron because it's a smaller atom due to a stronger effective nuclear charge. That would be the most complete answer. If you don't discuss the reason why using effective nuclear charge or electron shielding, you may not receive full credit on a quiz, test, or even the AP test. The last periodic trend that I want to talk about today is called electron affinity, and you can think of it as basically opposite of ionization energy. If ionization energy is the energy needed to remove an electron, then electron affinity is the energy released when an element gains an electron. The more negative the energy, the more likely or the easier it is for the atom to gain an electron. But if the number is closer to zero or even positive, that would represent a situation where it is not favorable for the element to gain an electron. The general trend is that electron affinities decrease, or in other words, get more negative going to the right. And we know this because our nonmetals prefer to take electrons. And so you'll notice on the next slide when I show a graph that the alkali metals have high electron affinities, meaning they don't want to gain electrons, they want to get rid of them. And so the halogens have very, very low or very negative ones, representing the idea that they want to gain electrons. It's the amount of energy released when the electron is gained. And going down a group, the affinity becomes more positive going down because the elements are larger due to increased shielding. And so that valence shell is further from the nucleus, and there's more electron shielding, and so the electron affinities are larger or more positive going down a group. So here's a periodic table of electron affinities, and as I mentioned, you get higher affinity moving to the right because the elements are smaller, the valence shells are closer to the nucleus, and the closer they are to the nucleus, the more attraction they feel to the nucleus, and thus the stronger affinity for those electrons. The nucleus wants to pull the electrons in closer. Those halogens are the smallest elements, or the second smallest elements, I should say, in a particular period, and so their nuclei are fairly close to the valence shell compared to something that's further to the left of the periodic table. And so as I mentioned, you get these high affinities in the right-hand side of the period. And going down, the affinities decrease because those valence shells are getting further from the nucleus due to increased electron shielding, as I mentioned. And the further they are from the nucleus, the less attraction they feel, and so the affinity is felt less. So negative affinities are good. You want electrons if you have a negative affinity. The more negative you are, the more you want electrons. And then a couple of them, you can see they have greater than zero, so they don't even identify a positive value for electron affinities. And as you would expect, noble gases have positive electron affinities because they don't really want electrons. They're full. And that next electron would go on a higher principal energy level, and that's just not likely to happen. They were more likely to get rid of that electron and keep their stable, full valence shell. You'll notice there's a couple of others that are at or about zero, like beryllium and magnesium. And this goes back to the concept that we talked about with ionization energy, that full orbitals are more stable than partially filled orbitals. And beryllium and magnesium actually have a full 2s and a full 3s respectively. And so they will have positive electron affinity. In other words, they do not want to gain more electrons because they are at a full orbital. Here's a summary of the periodic trends that we just discussed. The first one is atomic and ionic radius. The larger atomic and ionic radius are further to the left on a period and further down on the periodic table. Now again, this doesn't address the reasons why the trend exists. You need to know that the shielding and the effective nuclear charge affect atomic radius and ionic radius, and know how and why they are applied. Ionization energy, on the other hand, increases or is more positive as you move to the right or move up on the periodic table. Again, this is just the trend, this is not the why. Finally, electron affinity is more negative as you move to the right and more negative as you move up. Again, the reasons why are not listed, this is just the trend. Here's a common set of questions that you would see on the AP test that pertain to periodic trends. So take a moment to pause the video and see if you can answer these questions on a separate sheet of paper, and then go ahead and play the video and I'll go through the answers to each one. Potassium has a lower first ionization energy than lithium because potassium has one valence electron and lithium has one valence electron, but potassium's valence electron is further from the nucleus because it experiences increased electron shielding. Lithium's electron, on the other hand, is closer to the nucleus, and thus is held on tighter, and it would require more energy to dislodge that electron. Notice how I just didn't answer the question by regurgitating the trend. We know that potassium is lower because it's further down on the periodic table. And if you just say potassium has a lower ionization energy because it's further down on the periodic table, you will not get full credit for this on my test or the AP test. You need to address specifically principles of atomic structure. And by explaining the electron shielding, then you have addressed the principles of atomic structure. In letter B, you are now comparing the ionic radius of N3- and O2-, both of which have 10 electrons total, 8 of which are valence. But nitrogen only has 7 protons, whereas oxygen has 8 protons. And so you have an increased number of protons with the same number of electrons. And so O2- experiences a stronger effective nuclear charge, and thus the ionic radius is smaller. The answer to letter C. When you compare calcium and zinc, you first notice that they're both in the same period, the 4th period of the periodic table. And so they will experience the same amount of electron shielding. You might want to add that to your answer, but it's not necessary. Calcium is larger than zinc because zinc is further right on the periodic table, but that's not explaining using principles of atomic structure. You have to make reference to the fact that calcium has a weaker effective nuclear charge compared to zinc. Calcium only has 20 protons and 20 electrons, but zinc has 30 protons and 30 electrons. And the more protons and electrons you have, the stronger the effective nuclear charge, resulting in a smaller size. This last one addresses the anomalies you see when you're looking at a partially filled subshell versus a full subshell. Boron is smaller in size, and you would think that it would have a higher ionization energy. But because boron's electron is coming from a partially filled p subshell, beryllium, on the other hand, has a full s subshell, and a full subshell is more stable than a partially filled subshell. So that is why beryllium has a higher first ionization energy, or to answer the question, boron has a lower first ionization energy than beryllium. Well, that takes care of this video lesson. Thanks for watching.